So first thing we do is that we have to use this equation for x at t. So I'll make one change with it. We'll want to add in the phase of the harmonic. So just add a plus phi here, because for each signal you have a magnitude spectrum and you also have a phase spectrum. So a sum of sinusoid is basically just a sum of um, numbers where you have the magnitude and you have the phase. Okay, just magnitude and this is your phase. Just like the spectrum. So each sinusoid has a magnitude and it also has a phase. So you just write this plus phi as the phase of it. And this is the Fourier series expansion. So when we're doing this question here now, the first thing we have to do is let t be t minus d in this equation. So just go down here. So step one, replace t with t minus d, td. So you end up x t minus td as equal to the sum k is equal to minus infinity of infinity of ck e to the g plus k omega naught t minus d. And I have the plus 5 afterwards. So we have this. The next thing we do is we convert it to harmonic form. So to convert it to harmonic form, we just have to use this rule here. So we have this here, where we have the magnitude and the phase. And well, this is in the bracket. What you need to know is you're using the real part after you do the Eulers of this. You get this? And you're just using the real part. So you have the magnitude and you also have the angle. So whatever inside here is basically what on top here. So whatever in here is going back in here. And just using the real part as you see down here. So this up here will just become sum k is equal to minus infinity to infinity and ck cos k omega naught t minus td cos phi. And we can rearrange it a little bit. So we have k omega naught t cos phi and then minus k omega naught td. Okay, so we have this. So first thing, that's at face value, you can clearly see that nothing will happen to ck, but something will happen to the phase. Alright, so we know what, but let me just do a little bit more analysis to see what happens to it. So to do this, we just use a simple variable. So we'll have using the coefficient, the Fourier coefficients. So we want ck delayed, and that is equal to the Fourier coefficient not delayed and then multiplying that by e to the minus j k omega naught td. So how we get this? So this line here, we just converted it back to the exponential form. So you end up with the sum k is minus infinity to infinity of ck, and you'll have e. Since it's a plus, so it'll be whatever inside here, let's go back on top. So it'll be k omega naught t plus phi minus k omega naught td. And then we clearly see in that subtract, or we could say add. So when you're multiplying, you add the power, so you could technically split these exponentials up even more. So you get with e to the j k omega naught t plus 5, and then you have e to the minus j k omega naught td. So that's after you split it up. So now we have that. So this here, we're calling it ck no delay, or not delayed, because that is the original spectrum. Before we did it, this was the original spectrum. And this is the delay that we added, sorry, we multiplied in this case, or we included into the system basically. So that's how we got this here. So this ck delay is basically what we want to analyze. So the first thing we want to do, well, actually two things we want to do. We want to get the phase of the delayed Fourier coefficient, and we want to get the phase or the arguments of the delayed coefficient. So we could do that first. So the magnitude of ck delayed will equal to the magnitude of ck not delayed multiplied by the magnitude of e to the minus j k omega naught td. Well, this here just, we go back, which is here. So we have, oh, we forget to put about the ck. Let's just have a ck here. Right? So actually that is the whole thing that was supposed to be circled, because it needs to have a magnitude at least. Not looking weird, so I'm just write it over. So let's just have a ck here, and then it puts in back the summation sign. Yeah, so this here is what ck is, because you need the magnitude and also you need the phase. Okay, so we have to get to put the ck there, because this have the ck in it. All we did was split the exponentials up. Okay? Right, so that is what ck not delayed is, which is this here. It's so nice. So well, this here is ck, obviously, because from the form, this is the magnitude of it, and then well, the magnitude of this is 1. So we end up with ck. So what this means is that the magnitude spectrum for the delayed signal is exactly the same as the magnitude spectrum for the not delayed. That didn't change. So the delay didn't affect the magnitude spectrum in any way, shape, or fraction. So the delay did not affect magnitude spectrum. As we see here. So the next thing we need is the arguments. So that will basically be the arguments of ck not delayed, subtract the arguments at angle of 1 to e minus j k omega naught td. Well, we know the phase for this here is 5, right? Because that's what we had on top here for the phase. And well, this is basically just a constant, so it would just end up being minus k omega naught td. That is on top here, right? This is our phase components. And that's basically it. So the arguments is the phase, so this is the phase not delayed, which is the original phase spectrum, and a minus k TD. Okay, and that is basically all happened. So the next one is the MATLAB, and we will go through it. This code here, we have the time shift for one sinusoid. So we have the period is 1, omega naught, which is the fundamental frequency, 2 pi t, well, it's 2 pi and 1. A is the amplitude, which we don't really care about right now. And phi, we just using one sinusoid for now. So the phase of that one sinusoid is pi and 6, which is phi. Right? And td is your time shift. Oh, well, we don't really care about all that. So we can run it and see what it generates. Okay, so the first thing we want to look at is this. So the magnitude spectrum, well, we only had one sinusoid here, right? So we expect to see one side. Both of them, the original and the shifted, the magnitude spectrum never change at all. But for the phase, so this is what it was before. Remember, it was pi on 6. So it will be pi on 6. Yeah, that was what it was originally. So that is 5. So now you're subtracting. So it will be k, and this case k is 1. And you're multiplying that by your omega naught, which is 2 pi on 1, which is just 2 pi. And you're multiplying that by your shift, what the shift was 0.2. Yeah, and it should end up with this answer here. So that's basically what will be for one sinusoid. And if you have it for one sinusoid, and if you have more sinusoids, the only thing you need really is the original phase of the um sinusoid. Well, and once you have the original phase and you plot your spectrum, if it's k is 2, you basically just gonna go in and replace k as 2, and everything else will be the same. So remember, it's the previous phase minus k omega naught td. Okay, so you need the original phase spectrum, and for each of those, you're gonna be minus in k, which you will know what k is, based on where the spike is on the harmonic, by omega 0 by td, which is the equation that we have here. So we clearly see in that the magnitude spectrum never changed, but the phase was shifted. We have one, and well, we can clearly see in the graph that the one sinusoid was actually shifted by pi on 6. So just picture 20 more of these original numbers as sum of sinusoid. Each of them have a magnitude spectrum and a phase spectrum. The magnitude spectrum stay the same, but the phase will be shifted, and that shift is basically um, controlled by the index of k. Wherever k is, will determine the strength of it. Remember, omega naught and td are constants, and you can clearly see the magnitudes are the same. Okay, so that's how the first one was. And I do one more. So this one will have more sinusoids in it. So this one will have 5, I believe. So down here we can actually play around with the magnitude and the phases of each of the 5 sinusoids. Remember, so this one will be 1 cos omega naught t plus 0. And this one will be 0.8 cos omega naught t plus pi and 6, and the pattern will continue. And you're adding up all the sinusoids. Remember, it's a sum of sinusoids, each given in the magnitude and the phase of each of those. So magnitude is 1, phase is 0. Magnitude 0.8, phase of pi and 6. Magnitude 0.6,
phase of pi on 4, magnitude 0.4, phase of pi on 3, magnitude of 0.2, phase of pi on 2. That basically what it is. And you can express it in harmonic form like no, I add them up because it's a sum of sinusoids. We don't really care about everything else, so we can run the code. Okay, so I start with this one. So we expect it not to change. Because remember the magnitudes, we already had the magnitudes. Okay? So 0, 2, 3, 4, 5. We already had this. But there's just your magnitude spectrums at the particular harmonic frequency. I believe the fundamental frequency in this one was 0.5. Yeah, it'll be 0.5. Omega naught to be 2 pi and t is 2. Okay, so you should be able to get the fundamental frequency from there. But anyway, so let's see how the phase will look. So the phase, we expect the same shape. So the first one was 0, sorry, and then you have the other one which is at 1. Don't let this confuse you. So this is 1, 2, 3, 4, 5. So just express it in frequency. But it's still the harmonics that you deal with, because the fundamental frequency is 0.5. Okay, so we have this one here, and then same example, it will be here, what is values on top here, the original phase, which if we go back to the code, was pi on 6, so we can try it again, so it'll be pi on 6, subtract, and now we have here k, which is 1, multiplied by p omega naught, which is 2 pi on t, which is just pi, and you multiply that by td, which is 0.5, and we go back to your phase spectrum. Yeah, and you should get that value right here. So that's this is 0. Yeah, let's just check this blue dot on top. Right, so this is 0. So apologies. So the first value will be 0, not pi 6. Yeah, nice. So it worked out there. Remember, it was, when I go back to the values, the first phase was 0 and the magnitude was 1, right? So I used pi 6 there. So pi 6 was actually for 0.8. And we can actually try it here now. So this, the k here will be 1, the k here will be 2. So I could just go back and replace k as 2 and put the phase here now as pi on 6. And you could go back to the value. Yeah, and you should get this exact value here. And it was this on top. And we could just keep going. Let's try one more due to the length of the video. So the other one is 0.6 ampere and 4. So remember, this is the first harmonic, this is the second harmonic, and this is the third harmonic. So K will be 3. So you go back, make K 3. Remember TD, not gonna change. And the phase in this one is pi and 4. So you end up with, so we should end up with negative 3.9 something. Yep, exact. And well, the original one was pi and 4. And well, I mean, at this point, just better let's finish it and done. So the other one, so there's K 1, 2, 3, 4. So 4 is the phase, is pi and 3, and K is 4. So you end up with negative 5.23. Let me see what I have there. Yep, and then well, the last one, just for good riddance, K is 1, 2, 3, 4, well, 5. So K is 5, and well, the phase for the fifth one is pi on 2. and you should get minus 6.28. Yep, everything is perfect. So we have everything we need. So that's basically how the phase will look. And if you want to see how the actual graph would be, it will look like this. So the blue is the original, and then the red is your shifted or a delayed sum of sinusoids. So remember, this blue is made up of 5 sinusoids, as we saw in the MATLAB code. When you add those 5 sinusoids up together, you get this blue here. When you delay them, delay each of the 5, and you plot and you add them up together, you get this red here. So it looks different. Okay, and that's basically